Good afternoon, everybody.
Hello.
Hello there.
Hello.
Let's see where we're at in the schedule. Okay. Okay, so it's Thursday, January 28th. We are, yes, okay, so we've got 2 weeks until the test from today. And, we're on schedule here. So just keep that in mind. We've got the aromatic naming quiz is available. You should be doing that, or you should have already done that. Gotten the grade you wanted, hopefully. Okay, let's see. Okay, so we're dealing now with, I think, side chain reactions. Or diazidization. Okay. All right, so we're going to look at diazidization today. Then we'll look at some side chain processes as well. And then probably aromatic nucleophilic substitution. We'll get into that as well, I'm sure. Okay. So let's look at diazidization. And the usefulness of the diazidization process is that we can use a synthetic process to take a benzene ring we can nitrate it, and then we can take that nitro group and we can reduce it, so hydrogen and palladium, to give an NH2, and that NH2 group then can be converted into a diazonium salt, and then that can be treated with some sort of electrophilic species, I suppose, or yeah, electrophilic species. Actually, I shouldn't say that. It's a nucleophilic species.
Dr. Musgrave, could you please zoom in onto the PowerPoint? That's very small.
Okay. I'll do as much as I can. I'm trying to.
Oh, that's much better.
All right. Okay. So in nucleophilic species X minus, that replaces that N2, and there's a whole lot of X groups that we can put on there. So that's the utility of the diazidization reaction. We can take a benzene ring and put any of these different groups on there. CN, Cl, Br, F, OH, or I, or even put an H back on if we need to. So the process, or the key part of this process is the diazidization process, which uses nitrous acid, HNO2, which is nitrous, not nitric, that's why it's HNO2 here, that allows us to take that, and it has to be at 0 degrees as well. And that will allow us to take that NH2 to a diazonium salt, which can be reacted with all these different things over here in order to get our group that we need on there. So this is going to be what's part of the synthesis question for the test that you'll be taking. Now, the different X groups that we're talking about here, if you look at them, we've got CUX, where it's CuCl, CuCN, CuBr. You can see them over here listed. Can you see that on the screen?
Yes.
Yeah, okay. So you can be clear here that if it's CuX, that it's effectively Cu plus and X minus. The mechanism of the X minus reacting with the N2 plus, you can see it on the bottom here of the screen, where the X minus comes in, the electrons jump on the atom next door to the N2 plus, and then the minus comes in and kicks out the N2 plus. Now, this is not a reaction that occurs easily with most other things, but because we're forming a very stable leaving group, which is N2 gas, and the fact that that N2 gas can't leave the, well, it can't be brought back in. It leaves the reaction mixture as gas. So it's not like this can be reversed once it happens. So that's why it's a fairly favorable process, at least if we're using this kind of diazonium salt system. So let's look at the kinds of questions that you'll be asked about this, and I'll just pull up some old test questions here. So what I'm talking about here is the last question, question 7, I think it is. There we go. So this is the kind of thing that you'll be looking at. You won't see any of these questions as part of question 1. So what you've got is you've got a group which I would consider to be deactivating because it's got the C double bond O here, so we've got a delta plus, delta minus. So we know it's electron withdrawing or deactivating. And you'll notice where the OH is, it's in the meta position, which means that we can go through and do our synthetic process, which involves nitration, which will put it in the meta position. Then we can do the reduction, which is the hydrogen palladium, which makes it an aniline. And the diazonium reaction only occurs with the amine here, not anything else. Sorry, I want to do this. Let's put this over here first. There we go, that's better. And then you can do HNO2 and 0 degrees Celsius. Now, it could be HNO2 or it could be HCl and NaNO2 as well. I think on the slide I might even have HNO2 and HCl or something like that, but HCl and NaNO2 and 0 degrees Celsius might be another way you might see that expressed. And that will produce the diazonium salt, which has the N2 plus on it. Now in this instance we need OH. So according to the slide here, if we want an OH, then we use water and heat. So the entire answer there would be H2O and heat. And then that gets replaced with the OH. And that would be the entire answer.
Dr. Musgrave?
Yeah. Mm-hmm.
Where you have the, after we've connected the NH2 and then we have the HNO2 and the 0 degrees, down below it you have HCl and then NaNO2 at 0 degrees. Is that in the same process?
Yeah, that could be what you might see there instead of HNO2 and 0 degrees Celsius.
Okay.
You can see it either way. And so looking at the different species here and just being able to pick up the X minus out of each of them, I'll just go through each one individually. But that's an example of what you're kind of going to be expected to do. So CUX, yeah, you can see that's going to be Cu plus X minus, and that's going to be Cl minus, Br minus, Cn minus. We've got HBF4, and if you look at B is a metalloid, and it has a partial positive charge on it, so you can see that it's B like delta plus, which would lead to F minus. H2O is kind of like H plus OH minus. But again, there's your OH minus there. The H3PO2 is a reducing agent. It's equivalent to H minus. And Ki gives K plus I minus. So these are just ways that we can get these nucleophiles into our reactions. And these are all pretty much the final steps. So one other thing I'll point out here is that we can do this. We can do the diazotization step first and then throw in the X minus second, or we can do it this way as well, which might be preferable for some people because it saves a step. You can make it a two-step process. And that'll replace the NH2 with the X group as well. So either way is fine. Often those last two steps are done in the same pot anyway. So we don't usually form the diazonium salt, isolate it. We usually form it and then add the nucleophile straight in. All right, does anybody have any questions? So it's important this is done at 0 degrees. If we don't do it at 0 degrees, we end up getting a side reaction to occur, and that's this one. So you'll notice that this is what happens when we have NaNO2HCl at 25 degrees. This is room temperature. And you'll see that we end up getting what's called an Azo Dye as a product. In fact, these were some of the very first synthetic dyes that were created by chemists. Before this, dyes had to be extracted from plants, and it was very, very expensive. But once it was discovered how dyes could be created in the laboratory, they became a whole lot cheaper. So let's look at how this works here. So you can see that we have aniline, just standard garden variety aniline here. When we add the NaNO2 and the HCl to it, we do get the diazonium salt. But because it's at higher temperature, this diazonium salt can actually react with some of the unreacted aniline. This doesn't happen at 0 degrees, at least not to any great degree. So what happens is that we have our diazonium salt and it reacts electrophilically with aniline that hasn't been reacted to form the diazonium salt. Actually, I got the arrows wrong there. And that's how we're getting the joined ring systems that I've got here. Actually, let me take that out there. So I've still got that going. I should probably keep the double bonds in there for now. And that's how we end up getting our Azo Dye compound. Does anybody have any questions so far?
Dr. Musgrave, if you drew the mirror image of that, would that be considered wrong, or is that okay?
No, I actually have it at the top there. Do you see it on the slide?
Oh, okay, perfect.
Yeah, it's the same. It's the same one. It's just it's just reversed. But yeah, that's right. So either way, it'll work. Well, what's important here is that this is an electrophilic substitution that's going on here, but it's only happening because it's at higher temperature. Let's take a look at a couple of other examples of these, and you'll see it's not quite as complicated as it might look initially. You'll notice that this goes in the para position. This is because this is such a big group. It doesn't really like to go in the ortho position, but it could go, I suppose technically it could go in the ortho position, but it doesn't. It goes in the para position. All right, let's see, make sure I can get this right here. Yeah. So let's say I had something like this. This is terribly drawn. I'm going to have to erase that and draw it again. So I'm going to put two OMe groups on here, as well as the NH2. And then we'll treat this with HCl, NaNO2, and 25 degrees Celsius. So the first thing you can do here is just to draw. I'm not going to show the whole mechanism here because I got it over there. Let's see what the diazonium salt looks like. Then we need to recognize that that diazonium salt will add to the unreacted amide. And then you can see that the product would be like this. So if you break it up that way, it's a bit easier to see how you get the product. Does anybody have any questions? Any questions? Okay, do one more. What if we had something like this? So again, what I would do is I would draw the, I'd probably twist it around just to make it a little bit easier. Draw the diazonium salt. And then draw the initial compound. And that would give us this as our product. All right, anybody got any questions?
So for these, we would need to know them for number 7 and number 1, correct? On the test.
Well, number 7 would be the one that's at 0 degrees, Courtney.
Okay, so this would be
In this one you'll definitely see in number 1. One of these kinds of examples, yeah.
Okay.
But this is a side reaction. This isn't really diazotization as a
so
synthetic process.
the ones in the first chart that you gave us that were all at 0 degrees would be used for synthesis, correct?
Mm-hmm.
And that's the only ones we would need to know for synthesis.
For number 7, yeah. Mm-hmm.
Thank you.
Okay, side chain reactions. So there's a couple of side chain reactions we're going to talk about. The first one is oxidation. That's where we use some sort of very strong oxidizing agent to turn any alkyl benzene into a benzoic acid type situation. And it doesn't matter what alkyl group we use here. I mean, I could have anything hanging off here. It wouldn't matter. As long as there's an H on here, on this specific C, then we can, and I'll use the symbol for oxidation here. Doesn't matter, we end up getting benzoic acid as a product. The reason this ends up happening is because one of the intermediates is going to be a C dot attached to the aromatic ring, and this C dot is called a radical. Single electron species are notoriously unstable, but they can be stabilized at least to some degree by being next to an aromatic ring. So the fact that we can form that radical at all during the oxidation process means that we end up getting a carboxylic acid as a product, and it doesn't matter what else was connected to this as long as there's a CH here so that we can form that radical. Without the H there, it's more difficult to form that radical. The other possibility is the use of another compound called N-bromosuccinimide, NBS. And this compound allows for the formation of this radical specifically on the C by first of all forming a radical itself. So it's a radical initiator, if you will. And what happens is you can see the arrows there. They're actually half arrows. I'll try and draw them a little bit more clearly so you can see them. So that's NBS. And what I'm showing you there are two half arrows that produce these two radicals. So a dot on the N and a dot on the BR. And you can see there the dot on the N will form a radical by, they call it abstracting a hydrogen from the C that's attached to the aromatic ring. Remember, this C dot is somewhat stable, so it will form there. And then the BR dot can react with that C dot, and we end up getting this bromine attached to the C that has the dot on it. So I've got down here the little resonance structures that show why the dot on the C is kind of stabilized by the aromatic ring. It's because it can move around the aromatic ring. So you'll see this one on the test as well, the NBS reaction. I don't tend to put the KMNO4 one on because it doesn't have a mechanism, but because you can get a bonus point by doing the mechanism with the NBS, yeah, you'll see something like this on the test. Now keep in mind, this is the only thing you have to keep in mind with this, that if you've got an alkyl group attached to the chain or the ring, and we add NBS, the NBS will stick the bromine specifically in one location, and that is on the C next to the aromatic ring. Does anybody have any questions about NBS? All right, let's look at aromatic nucleophilic substitution. Now, aromatic nucleophilic substitution will occur only under specific sets of circumstances. Up to this point, we've been dealing with situations where we've got an electrophile E+ that can attack the aromatic ring, or the aromatic ring really attacks the E+, if you want to look at it that way. But in order to make it so that the aromatic ring will have an attraction to a nucleophile, how do we make that happen? Because, you know, this is negative to begin with, and now you're trying to add another negative to it. So how do we make it happen? Well, we can only make it happen if there are certain things that we put in place. In order to make this happen, we need a deactivating group on the ring in the ortho and para positions, or preferably in multiple ortho and para positions. If this happens, then the deactivating group can stabilize any negative charge that forms on the ring. So the other thing that we need the nucleophile needs to be a really strong nucleophile, and it has to be OH-, RO-, SH-, or RS-. Those are the most popular ones for this, because these are very strong nucleophiles. And again, the deactivating group that's on the ring has to be ortho and or para to where the chlorine is on the ring that ends up being replaced. So we also need the chlorine here as a leaving group, Cl-, and that's in that way we can get this to occur. So without the Cl, it certainly won't occur. And then we also need to have a strong nucleophile and deactivating groups in the ortho and para positions. So I've got on the next slide here what happens in that first step when the nucleophile attacks the ring with the chlorine on it. And you can see here that the negative charge, just due to resonance structures, ends up ortho and then para, like this. So let's say we had, I'm going to go ahead and redraw these a little bit. If I had a nitro group, in this position, you can see how that might be favorable, because now you've got the negative charge stabilized by the N+ on the nitro group. So as long as that's deactivating, then we can get a bit of stabilization here. But you'll notice that if we had the same situation and the nitro group was in the meta position, you'll notice that there's no way that the nitro group can stabilize that negative charge, because it's not underneath it. And if you look at the locations where the negative charge can appear, they can never appear at the meta position to where the nucleophile attacked the ring. So it won't work if the nitro group is not in the ortho or para position, or the deactivating group is not in the ortho or para position. So these are the requirements: a leaving group, Cl usually, at least one deactivating group on the ring, ortho para to a leaving group, and a decent nucleophile, something like OH-, RO-, SH-, or RS-. So if we look at some examples of these, so we'll have the Cl there, and then I can put, let's say, this and this. These are both deactivating groups. Remember that the C double bond OOME is like that. And then I can add something like this with the S minus on there and heat. And the product would end up being, because this would work with the S like this. Having replaced the Cl group. So that would actually go. Now I'll show you some answers that sometimes I see here. Can anybody tell me why this is not an acceptable answer?
The S has to go directly on the carbon that's closest.
But why? Why does the S have to attach specifically?
Because it has 2 valence electrons, so it has to have 2 bonds.
Well, that's
Otherwise,
okay.
Otherwise, the formal charge of S wouldn't be 0.
Okay, yeah, that's a more complicated answer of what I'm looking for, but there's a simpler answer than that, Mary. You're right. I mean, you're not wrong. But the pattern is that it's whatever has the negative charge. Whatever has the negative charge, that's what attaches to the ring. Okay? That's because that's what's doing the attacking. But yeah, that's it. No, your answer was good, Mary, but I'm just saying that yeah, the simpler answer is it's whatever has the negative charge that attacks the ring.
Right.
All right, does anybody have any questions? Okay, let's do some others here. Okay, so what do you all think of that? And you can see the conditions over here on the side. What do you think of that one? Will that give a product?
Yeah.
Maybe you've all forgotten in the last couple of days what a deactivating group and an activating group is. So the OH here is an activating group. So the answer there is no reaction. Okay.
Dr. Musgrave, would
Yeah.
you on the test that was a no reaction one?
Would I do it? Would I do it?
Yeah.
I could.
Okay.
I could. All right, what about this one? Now, I will give you a hint here. The NO2 group is a deactivating group.
Wouldn't that one also be no reaction?
No, it wouldn't actually. It would give you a reaction. Now, the fact that there's an NO2 group in the meta position, the NO2 group in the meta position doesn't do anything. It doesn't do any harm, but it doesn't do any good either.
Okay.
So this one actually would form a product because it does satisfy the requirements. Now, if you made that an activating group, that might not be such a great thing, but it is going to still work because it does satisfy the requirements. I just got tricky and put it there like that. There we go. So that would be the product. Okay, any questions?
So we need the activating group in ortho position or
Deactivating
para.
group. No,
I'm sorry, deactivating group. In ortho or para or
That's
both.
right. Or both. Yep.
Okay.
And if you can have them in all three positions, then it's even better, because you'll have that maximum stabilization of a negative charge.
Okay.
All right. Does anybody have any questions?
Yeah, I did forget about the activating and deactivating group. So can you tell me why OH is activating?
Okay, so if activating groups have this actually, let me see, have this characteristic. They have a delta minus on the atom directly attached to the aromatic ring, whereas deactivating groups have a delta plus.
Okay.
And that's ACT, yes. So that's ACT and that's deactivating. And what we noticed with the deactivating ones is that, generally speaking, they have a multiple bond to an electronegative element, and that leaves a partial positive on that X, and that makes it deactivating. So OH doesn't have that, so that's how you could know it's activating and not deactivating, Deanna.
Because it doesn't have multiple bonds.
Yeah.
Okay.
But anyway, that's a general thing. You can go back and look at that. It's in notes, but yeah, that's something that's important.
Okay.
All right. Any other questions about nucleophilic aromatic substitution at this point? Okay, let me see. So it's acidity. Okay, we're going to deal with acidity on Tuesday. We have a little bit of extra time, I think, in part because when we moved to a Tuesday, Thursday schedule, I gained a day because I didn't lose a day due to Martin Luther King Day anymore. So I'm kind of a little bit ahead here. So I'm going to use this time to talk about what you're going to see on the test here. Since we've gone through all the reactions now, and I can also give you a bit more guidance as to what to study and how to study, and what I recommend you do. But let's go back to question 1 here, and it'll actually be possible for you to. Oh, there's our nucleophilic substitution here. So question 1, these are the kinds of questions I'd expect to see. I would expect to see a nucleophilic aromatic substitution. That's what we just covered. Can anybody tell me if this one will go or not? What do you think? Is this one going to be a no reaction or what? Number 1 here. Am I still sharing my screen? Maybe you can't see my screen anymore. Is that the reason I'm not hearing anything?
No, I can see your screen. I just have never seen the COO. Is that ET? It's hard to see.
Yes, it is. Yeah.
Wouldn't those be? No, those would be that should go.
Yeah, that's they're deactivating groups. So that's what it would look like, couette, like that. So yes, those would go. So was it the fact that you couldn't see the double bonds? Was that the issue, or I don't know?
On the first one? I just can't see the screen very well. It's small.
No, okay, really?
The ET, that's ethanol?
Ethyl.
Ethyl?
Yeah. CH2, CH3.
Oh, and that's why it breaks up into that double bond.
Yeah. Let me see if I can make this a bit bigger.
If we redrew it to the point where like CL's was at the top,
That's
Yeah.
still correct. It's just
Yeah.
shifted.
Yeah, if you just shifted it around, a few degrees, yeah.
At the bottom, you can increase that zoom in, zoom out.
Oh, down here. Thank you. I was
Cool.
looking for it. All right. Is that any better?
Yeah.
Yes.
All right. Okay. Let me cross this out down here. Okay. So nucleophilic aromatic substitution. You'll get a Friedel-Crafts acylation with rearrangement. That one has a rearrangement. Yeah, you'll have the NBS reaction. You'll have a Friedel-Crafts without rearrangement. You'll have a diazidization side reaction or nitrous acid. I'll say diazidization side reaction. We went through this one today too. Okay. Williamson ether synthesis, a phenol reaction, which would be Williamson or Colby. And then the remaining ones will be generally second or third substitution. So I guess you'll have a third substitution reaction in there as well. And then the remaining ones will be second substitutions. Okay. So those are guaranteed. I mean, that's what you're going to definitely see as part of question 1. Okay. Does anybody have any questions? Anybody have any questions? This is about question 1. Does anybody have any questions?
Are those all in the blue book like last semester?
Well, not quite like last semester.
Like is there examples to do to practice?
There is, but not in the same way as they were available in Organic 1. So let me show you what you will have though. I know what you're talking about, Courtney, but it's not set up quite the same way.
Dr. Musgrave, for the test questions, do you want us to draw the whole entire mechanism as well, or just like the products?
No, let's go back to that. I'll answer that question before I show you the other stuff here. the way it's set up is that you can get a bonus point if you show the correct mechanism. But if you just show the products, that's what the points are for the question. So yeah, you can get a bonus point, but you have to show the exact, it has to be completely correct. You have to show the completely correct mechanism to get that bonus point.
Okay, thank you.
Okay, let's go to the problems I have here. There we are. Yeah, the way I had it set up in Organic 1 is I had separate reactions for each of these with the examples. I don't have that set up here. What I do have is the assorted examples. So now that you've been through all of them, you can practice each one of these. And I think going through them all it's not that big. I think it's might be a little bit more beneficial because then you have to figure out what kind of reaction you're looking at. Now, with that in mind, there is something else that does make that a little easier. Down the bottom here, a student prepared this for me and thought it might be useful to other students. I don't know how useful it is, but you might think it is. That's why I added it. I'm skeptical as to its usefulness, but I put it in anyway, begrudgingly. Here we go. So you can see that what they did was they went through and they showed what each of these reactions was. Okay. So you might find that useful. If you want to practice just certain types, maybe that's what you might look at, Courtney. If you said, I want to just practice this particular one, then you could go find them in the problems. You could do that. But we also have here the mechanisms, and these are the mechanisms for all of those problems, one per page. The complete mechanisms for each of them. So my advice about studying for this, and many of you are not going to like my advice, but this is the way I suggest you do it. Is that you do each of these and you do the mechanisms, and then you compare the mechanisms against the mechanisms in the test 1 mechanisms file. That's how I do it. I would do each of these. How many are there? 50. Right, so there's 50 of them. That's it. That seems to be enough. I mean, that's the feedback I've had, that for most people that seems to be enough reactions for them to work with. After you've done 50 of those, I don't think you really want to do any more mechanisms anyway. But then, you know, you compare them against the mechanisms here. That's how I'd study. And that's how other people have done it in the past. And generally the people who fail are the people who just don't do anything. They think they can just maybe do 2 hours of study and think that, well, that should be enough. That should about do it. No, you can't do that. You've actually got to work on the reactions, work on the mechanisms. The more you do with the mechanisms, the better you'll feel about them. All right. Does anybody have any questions?
Yes. So if I recall, this will be the first, because I wasn't with you for Orgo 1. So
yeah.
When you have the test and it's printed out, anything that you're going to allow us to have as far as reference material will be in what we can print out. Meaning we don't get to come with a 3x5 card with our cheat sheet stuff or anything.
No, that's correct.
Okay, perfect. I just wanted to confirm.
It's just like a regular garden variety class. I mean, you know, this is what I would allow in a test situation if I was giving this test in a class. I'm teaching the same material in pretty much the same way. I'm not trying to be defensive. I'm just saying this is how I've got it set up.
Now I noticed that the questions are presented just a little bit differently in like the test 1 problems here, or the blue book versus like the 2017 spring test that you keep showing us.
Mm-hmm.
They're just presented differently.
Are
it's
they?
the same
Well,
stuff,
I
though.
know it looks the same to me.
I think she means that in the book we have like the option to name it.
Oh, okay. Yeah. Well, okay. So yeah, there's no naming in the test because you got the naming quiz.
Got
But
it.
if you want to practice the naming, you can use that too. I would just ignore the name part of it.
Okay.
When you're doing it, especially if you've already done the naming quiz. But if nothing else, it's a reminder to do the naming quiz.
Dr. Musgrave.
Yeah. Sorry. Sylvia.
Okay. If you go to number 6 on that test.
Yes.
Please hold up.
I don't think we've done the material for that yet, Sylvia. We'll do that
Number
on
6?
yeah. Maybe. Let me see. Number 6. Oh, sorry. Okay, number 5 is one we haven't done the material for yet. We haven't done 5 yet.
Mm-hmm.
Okay, what about number 6? Yeah.
So for the middle diagram, you want us to label that as well?
Yeah. Yeah, I've given you the resources to do it, but you shouldn't need the middle diagram that much in order to solve the problem.
Yeah, so we can use either one, right?
Well, they're all for the same compound.
Okay. It's just I'm looking at the key for that you have up for that, and I guess the one you uploaded, each diagram was labeled, so I wasn't sure if you wanted us to do all of them or just.
Oh yeah, I want all diagrams labeled. Yes, it does say that if you look at the things here, it says showing the identity of all relevant peaks in each spectrum.
Okay.
So, for example, in the IR here, that's your C double bond O that I've got the cursor on, and over here that's the CH stretches. But again, you know, for background, you've got to watch those videos. You're kind of on your own with that, but that won't help you really solve the problem. It's going to be the proton NMR and the carbon NMR that will help you the most.
Okay, I got it. Thank you.
Okay. All right. Any other questions here about just about the test in general?
I have a question about the practice quiz for the acidity-basicity. Have we covered that?
No, I'm doing that on Tuesday.
Just wanted to make sure. Thank you so much.
Yeah, I'll do that on Tuesday. You could read ahead if you wanted, Victoria. It's pretty exciting stuff, riveting.
No. I have a lot to catch up on.
Okay. All right. Any other questions so far about the test or how to study or? All right, some people think that the best way to study is just to memorize the answers to the tests that I've given you. I don't think that's really the best way. I mean, people have done that in the past, but most of the people who've done that have not done so well. I'm just telling you. That's just my observation.
Just because you can doesn't mean you should.
Yeah. Well, I mean, I've given you my advice, and you know, people either take it or not take it. I'm old enough to learn now I have no control over anything except my own actions, and you know, you're going to do what you're going to do. I've become a little bit fatalistic in my old age, I think. People are going to do what they're going to do. Nothing I can do about it. All right. Anybody got any other questions or thoughts about test 1? So we just got that one other issue to cover, and that's for number 5, which I'll look at on Tuesday. And then yeah, so you know, the test was 2 weeks from today, so we've still got a fair amount of stuff. We've still got a fair amount of time before that test, so let's take it today. It's a good idea, Peter, but I don't think we'll do it today. All right. I guess, well, that's all I really want to do today. So I think we'll leave it there. Have a good weekend.
Have a good
Dr.
weekend.
Musgrave?
Thank you. Thank you, Dr. Musgrave.
All right. If anybody wants to hang around, ask me questions, I can.
Yeah, I have a question. I'm gonna wait.
Okay.